Assalamualaikum. Good day to all of you. In chapter 4, we have already learned how to solve second order linear differential equations, and actually these equations are used to model many situations in physics and engineering. In section 5.1, we are going to look at a very simple model, which is the model of the spring mass system. Even though this model is considered to be a very basic one, but it can be used to approximate other complicated situations. For example, we can use the model of the vibration of the spring to understand the bond between atoms and molecules. Let us now try to understand how the spring mass system works. This figure shows a spring suspended from a rigid body, and the spring is not loaded and therefore it is not stretched. When an object of mass m is attached at the end of the spring will be stretched by s unit long. So this is the object of mass m. And we let the mass to be at rest. The mass is at its equilibrium position because the force of gravity acting on the mass, which is F of g, balances the restoring force of the spring Fs. It is necessary to satisfy Newton's first law of motion to achieve equilibrium. The sum of the forces acting on the body at rest must be equal to 0. So this figure shows when the mass is at rest, two forces acting on the system, the gravitational force and also the restoring force of the spring. The gravitational force is equals to the product of mass and gravity, whereas by Hooke's law, the restoring force of the spring is equals to negative Ks. K is the spring constant and S is the stretch of the spring. The negative sign shown here is to indicate that the restoring force of the spring is always in the opposite direction of the displacement of the mass. By Newton's first law of motion, to achieve equilibrium, the sum of the forces acting on the body at rest must be equal to 0. In other words, summation of F is equal to 0. This implies that Fg plus Fs is equal to 0. Now Fg is mg, Fs is negative Ks, so mg minus Ks equal to 0. So at the end we get this equation, mg equals to Ks, indicating that the force of gravity acting on the mass at rest is equal to the restoring force of the spring. Let's get back to this figure once again. This mass is at rest. When it is at rest, the mass is at its equilibrium position. Let x denote the displacement of the mass. At the equilibrium position, x is said to be equal to 0. It is customary to adopt the convention that down is taken as positive, whereas up is taken as negative. So if the mass lies below the equilibrium position, then the displacement is positive. In other words, x is larger than 0. And if the mass lies above the equilibrium position, then displacement is taken to be negative. That is, x is less than 0. Now let us allow the mass to be displaced x unit from the equilibrium position, and then it is released. By Newton's second law of motion, there will be a net force acting on the system. So a resulting force causing the system to be in motion because the restoring force of the spring and the gravitational force are no longer balanced, causing the system to be in motion. So this is the mass displaced x unit from the equilibrium position and released. Assuming there are no other external forces acting on the system, so the mass starts to be in motion. By Hooke's law, restoring force of the spring is equals to negative K times x plus x, where s is the stretch of the spring and x is the displacement of the mass x unit from the equilibrium position. And gravitational force Fg equals to mg, and by Newton's second law of motion, the dynamics of the system are governed by the equation of motion, summation F is equals to ma. So summation F is equals to ma. Now summation F is the sum of the two forces acting on the system, the gravitational force and the restoring force of the spring. So Fg plus Fs is equals to mass times acceleration. Now acceleration is given by the second derivative of the displacement with respect to time. So d2x dt squared. Fg is given by mg and Fs is negative ks plus x. When we open up the bracket on the left side, we get negative ks minus kx. But from our discussion before this, mg is equals to ks. So if these two are equal, so the whole equation can be reduced to the following form: m d2x dt squared plus kx is equals to 0. Divide the whole equation by m, we'll get an equation d2x dt squared plus k over mx equals to 0, and this equation is known as the equation of a simple harmonic motion. The equation d2x dt squared plus k over ms equal to 0 is a second order homogeneous linear differential equation with constant coefficients. This equation is of second order, and x is the dependent variable and t is the independent variable. X represents the displacement of the mass, t represents the time. K is the spring constant and m is the mass. So this equation is said to be linear in x, and this equation has constant coefficients and it is homogeneous. The equation describes a simple harmonic motion, or we can also describe it as a free undamped motion. The motion has no retarding forces acting on the system. For example, there is no air friction that opposes the motion of the mass, and therefore we say the motion is undamped, and that the mass vibrates free of other external forces. So this figure shows the simple harmonic motion or undamped motion of the mass. Okay, so the mass is free to oscillate forever and ever, non-stop. Alright, so when x is positive, it indicates that the mass lies below the equilibrium position. When x is equal to 0, this indicates that the mass passes through the equilibrium position, and when x has a negative value, it indicates that the mass now lies above the equilibrium position. So this equation describes the simple harmonic motion or the free undamped motion. Let omega squared equals k over m. So we're going to substitute k over m by omega squared in the equation, so that the equation becomes d2x dt squared plus omega squared x equal to 0. To solve this equation, we have to start by forming the corresponding auxiliary equation, which is m squared plus omega squared equals to 0. This is a second degree auxiliary equation where we need to get two roots. Now this m here does not represent the mass, now it represents the root of the auxiliary equation. So solving this auxiliary equation gives us two roots. m1 is omega I and m2 is negative omega I. So this is a case of complex conjugate roots. The two linearly independent solutions are x1 is cos omega t and x2 is sin omega t. The general solution x of t is c1x1 plus c2x2, that is, x of t is c1 cos omega t plus c2 sin omega t. So this equation gives us the displacement of the mass x at any time t. This equation contains two arbitrary parameters c1 and c2. If initial conditions are provided, such as x of 0 equals to x0 and x prime of 0 equals to x1, these two initial conditions can be used to find the unknowns c1 and c2. Once we've got the values of the c1 and c2 based on the given initial conditions, then the resulting solution will be known as the equation of motion. The general solution for the simple harmonic motion or free undamped motion is found to be x of t equals to c1 cos omega t plus c2 sin omega t. We can actually rewrite this equation in another form, which is x of t is equals to a sin omega t plus p. Now these two equations are actually equivalent based on the sine angle addition formula. A is the amplitude of the free vibration, and the formula for A is equals to square root of c1 squared plus c2 squared. Whereas phi is the phase angle. Okay, so we can determine phi by using the formula tangent phi equal to C1 over C2, where C2 is not equal to 0. Now, if C2 equal to 0, then we cannot get phi from the arctangent of C1 over C2. So, if C2 equal to 0, phi is simply plus or minus pi over 2. The period T. What is the period? The period T is the time in seconds taken for the mass to execute one cycle of motion. So the period is given by 2 pi over omega, and the frequency f, which is the number of cycles completed each second, is equals to 1 over the period. Or in other words, this is equals to omega over 2 pi. So this graph describes the simple harmonic motion or the free undamped motion. A is the amplitude. It gives us the maximum displacement of the mass from the equilibrium position. So since this is a simple harmonic motion, so the value of A is constant throughout. T, the period, gives us the time taken for the mass to execute one cycle of motion. What about the case for a spring mass system in free damped motion? In other words, damping exists in the motion. Let us consider a mass suspended in a viscous medium where this medium opposes the motion of the mass. So therefore, a damping force acts on this mass. So damping force Fd is assumed to be linearly proportional to the instantaneous velocity dx dt. In other words, Fd is equal to negative beta dx dt. Now beta is known as the damping constant, or we can also call it as the damping coefficient. The negative sign here indicates that the damping force always opposes the motion of the mass. So let us now develop the model for the spring mass system in a free damped motion. Summation F is equal to ma. So there are three forces acting on the system now: the gravitational force, the restoring force of the spring, and the damping force. Add these three forces, and the sum of these forces is equal to mass times acceleration given by m d2x dt squared. The formula for the gravitational force is mg. Formula for the restoring force of the spring is negative ks plus x, and the formula for the damping force is negative beta dx dt. And the sum of these is equal to mass times acceleration. Rearrange and simplify until at the end we'll get this equation: d2x dt squared plus beta over m dx dt plus k over mx equals to 0. This equation describes a free damped motion. Notice that the beta coefficient exists here, showing that damping exists in the motion. There are three possible cases related to the damping of the system. The first case is the overdamped system. In this system, the beta or the damping coefficient is very large compared to the spring constant K. Due to this, the motion decays to zero without oscillating, and because the oscillation is suppressed by the damping. So these are the possible graphs of the displacement of the mass at any time t. For example, for an overdamped motion, there is no oscillation at all because the damping is too much, or there can be a maximum displacement for once and then the spring stops to oscillate, or there may be a one local minimum and the spring stops to oscillate after that. So for the overdamped system, when we solve the auxiliary equation, we will notice that the auxiliary equation will produce two distinct real roots, where m1 is not equal to m2, and the two linearly independent solutions are expressed in the form of x1 equals to e to the m1t, and x2 is equals to e to the m2t. And the general solution is x of t is c1x1 plus c2x2. The second case is on the critically damped system. In this case, the damping force is just enough to prevent the onset of any oscillations. It all depends on the value of the damping coefficient beta. If the damping coefficient beta has a value which is slightly smaller than the spring constant K, then some oscillations will happen. But if the value of the beta is slightly larger, then the motion will be overdamped. So the roots of the auxiliary equation for this case are real and they are equal where m1 is equals to m2, and the two linearly independent solutions are expressed in the form of x1 is equals to e to the m1t and x2 is te to the m1t. So the third case is known as the underdamped system. In this system, the damping coefficient beta is very small compared to the spring constant K. When we solve the equation for the underdamped system, the roots of the auxiliary equation are m1 is alpha plus I beta and m2 is alpha minus I beta. So we have a pair of complex conjugate roots, and the two linearly independent solutions are x1 is e to the alpha t cos beta t and x2 is e to the alpha t sin beta t, and the general solution is given by x of t is c1 x1 plus c2 x2. So this graph shows the graph of the underdamped motion, and notice that the motion is oscillatory. However, the vibration of this motion will finally decrease to zero because of the existence of damping. This second-order homogeneous linear differential equation with constant coefficients has its general solution containing the unknown parameters C1 and C2. Those parameters C1 and C2 can be determined based on the given initial conditions. So let us now try to understand the meaning of some statements given in some spring mass system problems in order for us to be able to quote the initial conditions. First of all, let us remember or recall this part here. When x equal to 0, it means the position of the mass is at its equilibrium position, and if the mass lies below the equilibrium position, it means that x is taken as positive, and when the mass lies above the equilibrium position, so x is taken as negative. So if the problem given in the spring mass system has this statement which says that the mass is released from the equilibrium position, then we should write down x of 0 equals to 0. It means that the displacement of the mass at the initial time t equals to 0 is equals to 0. If the statement says that the mass is released from a point below the equilibrium position, so it means that we have to write down x of 0 is larger than 0. Or if the mass is released from a point above the equilibrium position, then x of 0 should be taken as negative. The second initial condition relates to the velocity of the mass. So if the statement says the mass is released from rest or it comes to rest, that means the velocity or initial velocity is equal to 0. So we write down x prime, meaning dx dt, at the time t equal to 0 is 0. So the mass is at rest. It comes to rest, it is stationary. If the mass is released with a downward velocity, then we write x prime of 0 as positive. And if the mass is released with an upward velocity, then we write x prime of 0 as negative. Here are some examples. Question 1. A force of 400 newtons stretches a spring 2 meters. A mass of 50 kilograms is attached to the end of the spring and is initially released from the equilibrium position with a downward velocity of 10 meters per second. Part A, find the equation of motion in the absence of damping, and Part B, determine the amplitude, the period, and the frequency of motion. So to answer this kind of problem, we need to gather the information given in the problem first. So what are the informations that we got? Firstly, we are given that the force is 400 newtons, so we write F is equal to 400 newtons, and the stretch of the spring is 2 meters, so we use the letter S to denote the stretch of the spring, S equals to 2 meters, and the mass M is 50 kilograms. And this part of the sentence says the mass is initially released from the equilibrium position. So we are going to translate that into this form. X of 0 equals to 0. The displacement of the mass at the time t equals to 0 is at its equilibrium position, which is 0 meters, with a downward velocity of 10 meters per second. So downward direction, therefore the velocity must be positive. If this is upward velocity, then the velocity must be written as negative. So since this is downward velocity, we write down x prime of 0 is positive 10. If it is upward velocity, then you should write x prime of 0 is negative 10. Okay, so find the equation of motion. Before we have to get that, we are going to write down the general solution first. Now, the equation is given by d2x dt squared plus k over mx equal to 0. This is the equation of a simple harmonic motion, a motion which is free of damping. Okay, it says here in the absence of damping. So we need to know the value of the k and the value of the m. Now, fortunately, m has been given by this problem, which is 50 kilogram, but we do not know k. But k can be found by the formula of Hooke's law. F is equals to ks. Then k is f over s. K is 400 and s equal to 2, and therefore k is 200 meter per second. Okay, so you substitute the value of k and the m into here, and we solve this equation, use the auxiliary equation, and finally we get two roots and the two solutions, x1 and x2. So x1 is cos 2t, x2 is sin 2t, and now you can write down the general solution. X of t is c1 x1 plus c2 x2, or x of t is c1 cos 2t plus c2 sin 2t. Okay, so let's call this equation our general solution as equation number 1. Okay, we are going to label this equation for easy reference. Right, we are not done yet because there are two constants C1 and C2 that need to be determined, and we can find these two constants based on these two initial conditions. Okay, so this is the general solution which we have called as equation number 1. So first initial condition says that x of 0 equals to 0, meaning that at t equal to 0, the displacement of the mass is at its equilibrium position. So let us substitute t by 0 in equation number 1, and we let x is equal to 0. So from equation number 1, if t equal to 0, so we get c1 cos 0 plus c2 sin 0, and we are told that x of 0 is 0. Sin 0 is 0, therefore c1 times 1 is equal to 0, hence c1 is equal to 0. So since c1 equal to 0, we cannot substitute this value back into equation number 1, therefore this first term disappears. Therefore equation number 1 becomes x of t is equal to c2 sin 2t. This is the equation, and let us call this equation as equation number 2. The next initial condition is related to the initial velocity, which is given by x prime of 0 is equal to 10. So to use this initial condition, we should firstly differentiate equation number 2 first. Okay, so when you differentiate x of t with respect to t, we'll get 2c2 cos 2t. Once this is done, we can now apply this second initial condition where we are going to substitute t by 0 and let x prime of 0 as equals to 10. So substituting t by 0, we'll get c2 as equals to 5. And now we got c1 equal to 0, c2 is equal to 5, and therefore the equation of motion from equation number 1, okay, this is 0, so therefore x of t is 5 sin 2t. So this is the given equation of motion. To answer part B, we are asked to find the amplitude A. So to get the amplitude, we just apply the formula A is equals to square root of c1 squared plus c2 squared. Now c1 is equal to 0 and c2 is equals to 5. So A is equal to square root of 5 squared, which is 5 meter. And the period has the formula 2 pi over omega. Now 2 pi is equals 2 pi is 2 pi. Now omega is this part here, c1 cos omega t plus c2 sin omega t. That means omega is equals to 2. Okay, so omega is equal to 2, therefore the period is pi seconds, and frequency can be easily found by getting the reciprocal of the period. Frequency is 1 over t, or in other words it is 1 over pi hertz. Okay, so these are the answers for parts A and B for the given problem. Second question, a mass weighing 2 kg is attached to a spring whose constant is 32 Newton per meter. The medium offers a damping force that is numerically equal to 16 times the instantaneous velocity. The mass is initially released from a point 1 meter below the equilibrium position with an upward velocity of 8 meters per second. A. Determine the time at which the mass passes through the equilibrium position. B. Find the time at which the mass attains its extreme displacement from the equilibrium position. And C. What is the position of the mass at this instant? Okay, so let us try to gather the information given in this question. So firstly, we are told that the mass is 2 kg and the spring constant K is 32 Newton per meter. And we are told that there is damping in the system and the damping force is numerically equal to 16 times the instantaneous velocity. Now remember what we have discussed, damping force is numerically equals to the damping coefficient times the instantaneous velocity. So this is the damping coefficient, beta is equals to 16. And then we have this statement indicating the initial conditions given in the problem. The mass is initially released from a point 1 meter below the equilibrium position. So we write down x of 0 is equals to 1. X of 0 is equals to 1. So the position of the mass at time t equal to 0 is 1 meter below the equilibrium position. If it says the position of the mass is 1 meter above the equilibrium position, then we should write x of 0 equals to negative 1. With an upward velocity of 8 meters per second, so the velocity is in the upward direction, so the velocity must be negative. So we write down x prime of 0 is equals to negative 8 meters per second. So since this equation involves damping, so the model for this equation would be d2x dt squared plus beta over m dx dt plus k over mx equals to 0. Substitute beta, m and k in the equation. So we have d2x dt squared plus 16 over 2 dx dt plus 32 over 2x is equals to 0. Simplify and we get the auxiliary equation with two roots. M1 equals to negative 4, M2 equals to negative 4. So this is a case of critically damped because the two roots are equal and they are real numbers. Therefore, x1 is e to the negative 4t and x2 is te to the negative 4t. We now form the general solution. General solution is x of t is c1 x1 plus c2 x2. So we call this general solution as equation number 1. Okay, so we're going to find out the values of the unknowns C1 and C2 based on these two initial conditions. Alright, so the general solution is x of t is equals to C1 x1 plus C2 x2, where x of t is found to be C1 e to the negative 4t plus C2 t e to the negative 4t. Now given the first initial condition x of 0 is equals to 1, so what we have to do is to substitute t by 0 and let x equals to 1 in equation number 1. Okay, so from equation number 1 we have the following: x of 0 is equals to c1 e to the power of 0 plus c2 times 0 times e to the power of 0 is equals to 1. Now this term here certainly goes to 0 and therefore c1 is just equals to 1. So from equation number 1, after we substitute c 1 by 1, then we have the following equation: x of t is equals to e to the power of negative 4t plus c2t e to the power of negative 4t. So let us now call this as equation number 2. So there is an unknown c2 which we have yet to determine. So we can find it out by using the second initial condition, which is related to the initial velocity. Now given x prime of 0 is equals to negative 8. To use this initial condition, we have to firstly differentiate equation number 2 with respect to t. So when we differentiate equation number 2 with respect to t, we get the following: x prime of t is equals to negative 4 e to the negative 4t, and this part here we need to apply product rule of differentiation, which is after differentiating negative 4c2t e to the negative 4t plus c2 e to the negative 4t. Okay, so this equation for x prime of t, we are going to call it as equation number 3. So let us now apply the second initial condition given x prime of 0 equals to negative 8. So we need to substitute t by 0 and let x prime equals to negative 8 in equation number 3. Yes, so from equation number 3, x prime of 0 is equal to negative 4 e to the power of 0 minus 4c2 times 0 times e to the power of 0 plus c2 e to the power of 0 equals to negative 8. Okay, so from this equation, this term will certainly goes to 0. And solving this, we get c2 as equals to negative 4. So now let us substitute c2 equals to negative 4 and c1 equals to 1 into equation number 1. And from there we can get the equation of motion, which is x of t is equals to, okay, now remember c1 is equals to 1. So e to the negative 4t and c2 is negative 4. That will be negative 4t e to the negative 4t. Okay, so this is the equation of motion related to the given problem. So the question for part A is that we need to find out what is the time when the mass passes through the equilibrium position. So the mass surely will pass through the equilibrium position when x of t equals to 0. Okay, so now we're going to find out the value of the time when x of t is equals to 0. So what we have to do is to use the equation of motion and let it be equal to 0. Okay, so x of t equals e to the negative 4t minus 4t e to the power of negative 4t. Solving this equation, we get 4t e to the negative 4t equals e to the negative 4t, implying that t equals to a quarter of a second. Okay, so it means that it takes a quarter of a second for the mass to pass through the equilibrium position. For the second part, B, we need to find out the time when the mass attains its extreme displacement from the equilibrium position. Okay, so the mass attains its extreme displacement from the equilibrium position when x prime of t equals to 0. Therefore, we need to differentiate the equation of motion, okay, with respect to t to get the answer. So this is the differentiation. You get negative 4 e to the negative 4t minus, here you apply product rule of differentiation, get negative 4 e to the negative 4t plus 16t e to the negative 4t. Okay, so this is the x prime of t, and the mass attains its extreme displacement when x prime of t is equal to 0. So solving this equation, we get t as equals to half of a second. Okay, so what does it mean? It means it takes half of a second for the mass to attain its extreme displacement from the equilibrium position. Okay, so in part C, we need to find out what is the position of the mass at this instant. In other words, we need to find out what is the position of the mass at the time t equals to half of a second. Okay, so what we have to do is to substitute t by half of a second into the equation of motion. So we get x of half is equals to e to the negative 4. Now replace t by half minus 4 times a half e to the negative 4 times a half. Okay, now solving this equation, we'll get x of half is negative e to the negative 2 meters. So what does it mean? It means that the negative sign indicates the mass lies e to the negative 2 meters above the equilibrium position. Okay, so this sign here indicates the mass is above the equilibrium position, but if the sign is positive, it means the mass is lying below the equilibrium position. So that's the end of the lesson today, and so I hope you can understand all the discussion given in this chapter, and thank you very much.